Hello and welcome. Thank you for participating in Morehead at Home Skywatching, hosted by Morehead Planetarium and Science Center. My name is Amy Sale. I'm an educator at Morehead. We are a unit of the University of North Carolina at Chapel Hill, located on campus. We also work throughout the state through a number of outreach initiatives like our mobile lab van, summer camp programs, and the annual North Carolina Science Festival. Our mission is to help people better understand science, technology, and health, and we do this through engaging learning opportunities like this live virtual event. We're happy to have you here with us today for our topic, Supernova, and Nick will get us started.
Thanks, Amy. And hello, everybody. Welcome to Morehead at Home Skywatching. We're excited you're with us today. This is a very exciting topic, so we're excited to dive in and start talking about these really mysterious and beautiful and exciting events in the universe, so supernova. First things first, though, we want to let you know that if you have questions throughout the session, we want you to ask them. But the best way to ask them is by using the Q&A function, which is right down at the bottom of your screen. You can type in your questions there, and we're going to try to reserve some time at the end to answer a few of those. So be thinking if you have something you'd like to ask. We also will be sharing a number of images and videos and things like that today. So we hope you enjoy them. And if you haven't been with us before, we're also going to be doing some poll questions. So you'll be able to participate that way and maybe give us some of your answers to those questions as they come up. But I think we're probably ready to get started. So our first real big thought here is, what is a supernova? We said that that's what the session is all about, but Amy, how would you define a supernova?
So my quick definition would be a supernova is an explosion that happens when a massive star reaches the end of its life. We're going to go into a lot more depth about the life cycle of stars on Thursday, so that's a shameless promotion there. Join us on Thursday. But we'd like to start you off with a poll question. So we want to get your ideas on this. It's a true-false question. And the statement is, the sun will eventually go supernova. If you think that is a true statement, select true. If you think that's false, select false. I'll give you a few seconds to think that over and discuss it with anybody who might be watching with you. True or false, the sun will eventually go supernova.
That's a good clarification to make, that stars have lifetimes. We will kind of be talking about that today and diving deeper on Thursday, but remember, the sun is a star. So is its fate to go supernova? We're curious to see your answers here.
Okay. A few more seconds. Oh, there we go.
Whoa, okay. It's a pretty good split, Amy.
Yeah, a lot of you thought the sun is going to go supernova. What do you think, Nick?
You know, the sun is a star, as I just said. I didn't mean to spoil your answers or anything like that, but it turns out that not all stars are candidates for a supernova. And the sun is not the type of star that's going to go supernova. It is going to change throughout its lifetime, but it is not the type of star that's going to have this really massive explosion. So the answer with that one is false. The sun is not going to go supernova, which, might help us sleep at night a little bit better, even though these things happen on really, really big time scales.
Right. So you got to be a massive star to go supernova, and the sun is just not massive enough. So mass determines the fate of a star. And are we ready to share some images?
We are, yeah. And so the first image that y'all are going to see as I share this is an example of a star that is massive enough to go supernova. What you should be seeing on your screen now is it's an artist's depiction of a star that we've talked about before in Morehead at Home called Betelgeuse. Some folks pronounce it Betelgeuse, but I usually say Betelgeuse. I almost said it 3 times in a row there. That would have been bad. But this star is different than our sun. It's way, way larger than our sun. And let me explain this image to you so that this makes sense. Right now, it kind of looks like Betelgeuse has big rings. But really what's happening is our solar system is superimposed on this artistic image of the star. So that circle right in the center, that is supposed to represent about the size of our sun. So the largest thing in our solar system is represented as kind of a tiny smudge on such a large star as Betelgeuse. And then what you're seeing here with the rings, these are the orbit lines of the planets in our solar system. So maybe that first line is Mercury, Venus, Earth, well within Betelgeuse's atmosphere there, Mars, and then you can see Jupiter, Saturn, and even Uranus and Neptune are not labeled, but their lines are there. So you can see that there are stars larger than the sun, and this one in particular would take up most of the inner solar system almost out to the orbit of Jupiter, just in diameter.
And Nick, I'm peeking ahead at the questions people have started to ask, and I see that Bill has a question about which star most likely to go supernova. Betelgeuse is definitely a candidate for going supernova soon, and soon could mean tomorrow or 100,000 years from now.
Yeah, that is the tough things with star lifetimes. They live for billions of years. So Betelgeuse is the right mass. It is pretty old. It's in the period of its life where it could happen. But again, that could be later tonight or 10 million years from now. That's all still pretty small on the star lifetime scale.
Okay, what do we have next?
Yeah, so we do have some historical precedent and some other images to show you. This one is really neat. This is an X-ray image of the Tycho Supernova Remnant. So deep within this really colorful blob here, a star exploded and sent its material, its gas, out into space around it. And the Chandra X-ray telescope, along with some other processing, was able to capture this image of how material is moving away from what used to be a star.
That's a supernova remnant. When I first saw this image, Nick, I thought it looked like coronavirus and bubble wrap.
Yeah.
But it's something much bigger, actually.
Much bigger.
And it's in outer space. Okay, and I think we have a story to tell you all, a true story about a star that went supernova. Okay, so this is an image from Chaco Canyon in northern New Mexico. And I want to tell you a story about what probably prompted this image. On July 4th, there were fireworks of a sort in the sky way back in the year 1054. So roughly 1,000 years ago, Chinese astronomers, and it also appears some people native to the southwestern United States, observed a star in the sky where they hadn't even noticed a star before at all. And it was so bright. It was seen at night where it had never been seen before for almost 2 years. And it was so bright, it was seen in the daytime for 23 days. The star was quite a bit brighter than Venus. And it turns out what had happened was a star had reached the end of its life and had gone supernova. Now, the star is actually, it turns out, really far away, 6,500 light years away. So by in 1054 was when the light reached us. The event had actually happened thousands of years in the past, even at that point. And so what you're seeing here is a pictograph in Chaco Canyon. It's on a trail that you can hike. And you see what looks like a human hand at the top. On the bottom left, you see the depiction of the supernova, of the star exploding. And then, Nick, what do you think that thing on the right is? Kind of looks like a horseshoe.
Yeah, it kind of looks like a horseshoe, but I bet they were trying to draw a crescent moon.
Yeah, so if we have time, at the end of the program, we actually want to use Stellarium, which is free Planetarium software, to replicate July 4th, 1054, and see if in fact is the moon close to that part of the sky. Okay, so 1054, what was seen was this apparently new star because it was a supernova explosion. And then images have been made of that. I think we've got an image from, what is this from, 1844?
Yes.
So somebody drew this picture of what they thought it looked like. And then we've got a more modern day image. And this is what we see now. And this is, a heavily processed telescope image. You're not going to see this when you just glance up at the sky. This is called the Crab Nebula, and it is a supernova remnant. So this is what we see 1,000 years later. And images have been made over time of this remnant, and it is still expanding. You can actually see a time-lapse video and actually see that it's still expanding. So this is the Crab Nebula, also known as M1, the first object on Charles Messier's lists of objects that look sort of fuzzy, maybe like comets, but were not comets.
Yeah, and this is, one of the most famous images from space. I think it's incredibly beautiful. But Amy made a really good point that this image we have is just a snapshot in time. For the last 1,000 years, the shape and structure of this, what became a nebula after the supernova explosion, has changed, and it will change into the future. So it's kind of neat to continually look deeper inside, and that's actually what this image is. We have a big, broad picture of the Crab Nebula, but we've used telescopes to gaze even deeper within this, and they think now where the supernova originally happened inside of this region of space, there's now a pulsar that's left over and kind of sending its energy and affecting the space around it, which is kind of what you see here with all of these ripples. So it's kind of neat that 1,000 years ago we have a depiction of the supernova, and as we move through the centuries, our knowledge of it and our picture of it starts to get deeper and deeper. So let's talk a little bit about what all this stuff is that's moving outward when a star blows up. Stars are made almost completely out of gas, but depending on their age and their size, so some different things are happening inside of the core of a star. So for some of us, this image might look familiar, or it might look a little funky. This is the periodic table of the elements. You might not have known you're going to get a short chemistry lesson today, but many of the chemical elements on this chart that you learn in school, or might not have learned in school quite yet, are formed within the furnace, within these very energetic explosions of stars. So a supernova is actually one of the ways that some of these elements get out into the universe. So you can see we have a legend here that kind of goes by color that tells you where things come from. But the ones we want to focus on are dying low mass stars, exploding massive stars, and exploding white dwarfs, and merging neutron stars. Most of these are what we talk about when we talk about a supernova. So you can see that things like H for hydrogen and He for helium, those came from the really, really early universe. Those are some of the most abundant elements we see out there in space. And they're what makes up most of the mass of a star. But as you move up the periodic table and start getting to things like carbon and nitrogen and oxygen, the things we know we need for life here on Earth, those elements are getting heavier. And we have to try to think about how these heavy elements can appear out in our universe. And scientists have figured out that you need a big source of energy, like something that we see with a supernova, to be able to create some of these heavier elements and that we see here on Earth now. So Carl Sagan, my favorite astronomer, has this quotation that I always think about here. He says that the iron in your blood, the calcium in your bones, the carbon in your apple pie, were all forged inside the furnaces of these dying stars. So you might have heard before that you are star stuff. Well, all of these chemical elements that we see are also star stuff. So when we talk about what things are made of, what matter is, we're talking about stuff that was made inside of stars. So even though it kind of sounds sci-fi, you are made of star stuff because you're made of these same elements.
Wow, that's pretty amazing, Nick.
Yeah, it's a big thought. And, we have some more images of remnants that we found of supernovae, but I know y'all are probably curious, how does this happen? We talked a lot about like how we can see it and that we've seen them throughout history, but let's talk a little bit more about the science of how a supernova happens. And we have a kind of neat way to do that for you. We're actually going to show you a video clip. So here we are. We're going to simulate the explosion of a massive star. So just a disclaimer, this isn't a live video. It's not an image taken by a telescope or anything like that. It's a simulation. But what do you think, Amy? Should we dive within the star here?
Let's go. Let's safely dive in with our really special spacesuit.
Okay, here we go.
Pretty hot in here. Okay, diving into the outer atmosphere of a red supergiant star. It's nearing the end of its life. And I think we're going to try to go all the way to the core. Okay, this is where nuclear fusion happens. The star is fusing atoms into heavier and heavier elements, creating some of those elements you see on the periodic table. But iron is where the fusion process stops, and the core can't hold itself up anymore, collapses under its own weight, and then there's this explosive shock wave that ends up exploding most of the star into space. And then what remains of the core collapses, and in this example, becomes a neutron star. There's enough mass it can actually become a black hole.
Yeah, and that would probably take a whole other lesson to kind of talk about all the intricacies of these differences. But hopefully that trip inside the star gave you a little bit more of a visual, because, you know, human beings have never been able to get that close. So again, we're making our best guess what it looks like deep within a star. And a good point that, you know, you might have seen there and Amy mentioned is that stars fuse elements together. Mostly hydrogen and helium, but then eventually as they get older and bigger, they start to fuse other elements together. And that's how stars release their energy. So you see that everything is kind of a balance between the energy being created within a star and the gravity pushing down. And when you lose that balance, certain types of stars can explode. And that's where that supernova comes from. But I think we have another way to help connect this idea. And this is something that y'all could even try at home. So I'm going to navigate us one more time to a web page you might have seen before. This is NASA's YouTube page. And we wanted to share one more video with you before we kind of look at some supernovae in our sky, or where they might be in our sky. This lasts about a minute and a half. You should be able to hear the sound on your computer. But this is a demonstration that you can even try at home to think about how energy is released in a supernova. So if you're ready, Amy, I think we can go ahead and play.
Let's do it. And we do encourage you all to try this at home afterwards.
Okay, here we go.
This is a very simple activity that models the supernova explosion that takes place at the end of a large star's life. The only supplies you will need are 2 balls of different sizes for each person that is participating. A tennis ball and a ping pong ball are perfect for this. If we drop just the tennis ball, it bounces a foot or 2. If we drop just the ping pong ball in the same way, it again bounces, but not as high. When we drop them both together, with the ping pong ball stacked on top of the tennis ball, the ping pong ball goes flying off even further, and the tennis ball basically stays where it is. The reason this happens is that when the tennis ball hits the floor, its energy is transferred to the ping pong ball. In this model, the balls represent layers of the star's atmosphere that are falling inward during its implosion. These falling layers meet the energy from the iron core, represented by the floor in our activity, and rebound, shooting off into space in a dramatic supernova explosion.
Okay, I think that's really cool. Another disclaimer, stars aren't filled with ping pong balls and tennis balls, but the idea is that we want to see how that energy is transferred. So for our purposes here, we can even show you an example, because I happen to have those 2 things right here in my house. Regular tennis ball, regular ping pong ball. And we can even see if this works here on my desk. No promises. I do want to give you a disclaimer that it kind of matters how you hold these things. So you might have noticed in the video, one of the educators was kind of holding it wonky, and it looked like it kind of went off in a different direction. So safety first. You know, you want to make sure to not be near anything that's really breakable, and you want to make sure to kind of do this away from yourself, so you're protecting your eyes and things like that. But we can show you. I know you can't see where it's going to hit, but see if you can keep your eyes on the ping pong ball here and see if we can just make it launch into the air. So imagine we're deep within the core of a star and we're going to have a supernova. So I'm going to drop it one way that I like to do it. This is how Amy likes to do it too, so that they drop really at the same time, is from right above. But for the purpose of you guys being able to see it, I'm going to do it from the side. Okay, so here we go. You want to give me a countdown, Amy? You're muted.
All right. 3, 2, 1. Supernova.
Whoa.
Oh, that was good.
Cool. Okay,
Oh,
well, I
excellent.
didn't break anything at my desk, so that's great. But you see, it's a simple way to see how that energy is transferred. And this is just happening on a really big scale when we are talking about stars.
And you all definitely do try this at home. You may want to do it. It doesn't work so well on carpet. So if you try a tile floor or a wooden floor, or even better, maybe outside on a sidewalk or on a road where there are no cars. You can also, if you're feeling brave and you happen to have a basketball available, it works really great with a basketball and a tennis ball. So you might experiment with whatever you have. And if you are very young, we recommend that you have adult supervision for this.
Yeah, most
definitely.
definitely.
And it can be tricky. I want to say it can be tricky. We've done this activity a lot of times at like UNC Science Expo and other skywatching events and things. It can be a little tricky to get the balls to fall at exactly the same time. So don't give up if it doesn't work right away. Keep trying it out. Maybe ask somebody else to help you. See if you can figure out how to get the balls to fall at exactly the right time. And then that ping pong ball or smaller ball will really bounce off. It's pretty fun.
Okay, so we're gonna try it again because I saw your comments there that the camera was on Amy because she was talking, and you didn't see the ping pong ball go into the air. I'm sorry about that. So you know what? We got nothing but time here, so let me go hunt down this ping pong ball real quick, and we'll try it one more time. Okay, give me 2 seconds.
Okay, and I will stall for time here. I'm going to look through your questions really quickly and see if there's one I can answer while Nick is tracking down the balls. Kim asked, what would be the effect on Earth if Betelgeuse went supernova? Well, we'd have a really cool sight in the sky because it would be, you know, like as bright as a gibbous moon. That would be amazing. It will not hurt us though. Betelgeuse is really far away. You would not want a star close to you going supernova, but there are no stars close by that are supernova candidates. So that's good news. Okay, Nick, I think I might even turn my video off while you do this in hopes that it won't flip back over to me because I've noticed.
We'll give it a try, and maybe I'll just do the countdown myself, and that way you guys can see it. Okay, so thank you for suggesting we do this again because it's one of those things that's easy enough just to try again. Remember, tennis ball, ping pong ball, we are transferring the energy. Right now when it's up here in the air, it has potential energy to go towards the ground. We're going to see if we can move some of that energy into our ping pong ball or the outer core, the outer layers of our star. Okay, so here we go. We're going to drop in 3, 2, 1. Ah! Well, supernova came right at me that time, but hopefully you guys got to see it. And again, try it out yourselves. Be safe while you do it. Hopefully you saw it a little bit better that time, though.
That was excellent.
Okay, don't worry.
Thank you, Nick. You look uninjured.
Okay, so I see so many great questions in the chat, but we did want to have one more segment of this to kind of connect some of the ideas we've been talking about. We want to show you the nighttime sky. Obviously, that's something that Amy and I love to talk about and love to do, but we have some neat examples of stars that are candidates for supernova in our sky. So we're going to share one more time so that y'all can kind of follow along with us in Stellarium. And let me adjust my window here so that y'all can see.
And if y'all look in the chat, you'll see that we've added the URL. You can download Stellarium for free. It's STELLARIUM.org.
Okay, so we're here in a daytime sky. We do see an example of nuclear fusion happening right there in the sky, our sun. But again, we already determined our sun's not one of those candidates to become a supernova. So in the interest of time, we need to make it nighttime. And if you've never seen the Stellarium screen before, I'll let you know that we're facing south. The top of the sky, the zenith of the sky is going to be right up here above you. And I'll even pull us out just a little bit here so that we can see the western horizon and the eastern horizon as well. But unlike the real world, we can speed up the clock down here and move towards nighttime. So I'm always happy to give a lesson about how things are moving, even though it looks a lot like the sun's moving across the sky. Always remember that really we're the ones that are moving. The Earth is rotating. And that's going to change how things look up there above us. So you know that we just passed our summer solstice, the longest day of the year. So our sunset time is going to be pretty late this evening. And you know we're down here at about 9 p.m. We still see a glow, but then we have a nice dark sky. Okay. So what do you think, Amy? What should be our first star that we look for?
Why don't we, let's look for Antares because it's a supernova candidate. Antares is a reddish star in the constellation Scorpius the Scorpion. And so it's hundreds of light years away. So when it eventually does go supernova, it poses that radiation coming out from the star won't pose any problem for us. And actually a number of the stars in the constellation Scorpius the Scorpion are supernova candidates. They are massive enough that they will eventually go supernova. A fair number of the stars that you see in the sky are massive enough to go supernova. You got to have something like 8 times the mass of our sun. Somebody asked a question about that to be able to go supernova. And you might think, well, is it that most of the stars will go supernova? It's more that preferentially you are able to see stars that are more likely to go supernova. Kind of like when you look at an airplane at night flying over, there's some bright lights on the outside of the airplane that are easy to see, but there's actually lots of lights inside the airplane. The cockpit lights, people using the reading lights, but you don't see them as well, even though they're there. So that's kind of what goes on with stars. Certain stars are easier to see than others.
That's a really good point. And we'll dive more into that on Thursday because the size of a star, its mass, its luminosity, all of that affects how bright it is to us here on the Earth. So, okay, we have Antares. What's another?
There's a star that's a nice, safe, faraway distance in the Summer Triangle that's going to go supernova. The Summer Triangle consists of, you might imagine, 3 stars making the points of the triangle. Vega and Altair are relatively close to us. We wouldn't want those to go supernova, so it's good that they won't. But Deneb, far away, will eventually go supernova. It's a massive star.
And Deneb is the tail of Cygnus the Swan. So if you're making the triangle, that's between Vega, Altair, and Deneb.
Okay, and then maybe we can, I know we're about to run out of time, maybe we should just go straight to the Crab Nebula?
Yeah, let's do that. So we have to do something kind of interesting to get us to the Crab Nebula because it's usually visible in the wintertime, or most visible for us in the wintertime. So we're actually going to move all the way to the daytime and then use a little bit of planetarium magic to make it so that we can still see things up here.
Oh, Nick, do you think we still have time to show people Betelgeuse?
I think we do.
Okay.
So here's something that will never happen in your real sky. We have this beautiful blue sky. We're going to take it away so that we can see what things would look like in the daytime. And you see now probably why you can't see Betelgeuse. It's in the same direction as the sun right now from our perspective. But there's our friend that we talked about who is on the verge of blowing up.
Which means, tomorrow or 100,000 years from now, we don't know. Again, will not hurt us when it happens. It's really far away. So, and we did a session recently called Where's Orion, which answers the question of why you will not actually see Orion in the night sky tonight because it's up in the daytime at this time of year. Yeah. But it's in Taurus that constellation of Taurus where all the action happened in 1054.
Yeah, so how about this? The sun is kind of in the way right now. This is a little bit of a weird view. Let's travel to 1054. And we can look at the Crab Nebula and where it is that way.
This is a fun thing about Stellarium. You can change, so we have it set up, you can change it, the date, the time, and the location. And so just for simplicity, I imagine we'll probably stay in North Carolina, but we can change the date.
Okay, so just like that, you time traveled almost a whole millennium into the past. This is 1054 AD on July 4th. And let's zoom into this particular part of the sky. Again, this is daytime. The sun is up, so I'm going to do that magic again and take away our sun. But you might remember from our artistic representation on the cave wall earlier. What do you think? Is that a crescent moon right there?
Yeah.
Okay, well, let's try to keep it in the picture here, because the Crab Nebula is kind of in, I always think of it as kind of in between Betelgeuse and Aldebaran, but higher up. It's kind of like near one of the horns of the bull. And, you know, I don't want to click on the wrong thing, so we're going to do this the easy way and find
You can search for
M1.
things in Stellarium. You don't have to just already know where everything is.
So if you had a telescope and you pointed it in this direction, today, this is where the Crab Nebula would be. I know we're here in 1054, but Stellarium doesn't have a representation of exactly what the nebula looked like or the Supernova Remnant looked like. So this is how it would look today. You need a telescope to be able to see it.
It's like a little fuzzy thing now.
Yeah, if we get
So
close.
I know we're running. Oh, there we go. Good. Thank you. We got to look. So this is a fun thing about Stellarium. It does have representations of many objects, and you can zoom in and see them. We're about out of time. I was thinking we might want to sum up really quickly and then see if there's a question or two.
Sure. Yeah, so thanks for bearing with us as we showed you so many things. It's a complicated thing to think about how stars end their lives, but there are examples in your sky, and it's possible that in our future we see one of those remnants in the sky like they saw 1,000 years ago. We just don't know exactly what that will look like.
And this might be the time we pop up the poll question to find out how many of y'all are watching this. If you can answer this question, that would help us a lot with collecting our data. So we're wondering how many people are watching this program on your screen right now. Is it just you, so one person, or are there 2 people watching, 3, 4, or 5 or more? You can let us know that. That would be very helpful.
And I see some great questions here, Amy. From Hema, there's a question that says, what's the force ripping helium into hydrogen? And I actually like that question, but it actually works a little bit differently. Inside a star, instead of ripping apart helium to make hydrogen, you're actually combining or fusing hydrogen to make helium. So there's a difference between what happens in, say, a nuclear power plant here on the Earth. Here on the Earth, we call that nuclear fission, and that means you're taking apart the atoms and releasing energy. But in a star, it does something called nuclear fusion, where those atoms come together and release energy. So I know that can be kind of confusing that they both release energy in a way, but in a star, the force that's doing it, to answer your question, is there's intense pressure and gravity deep within the star that it makes those particles really, really energetic, and they have so much energy and there's so many of them that they have a higher chance to whack into each other and fuse and release that energy. Okay.
Thanks, you all. We are out of time. So we hope you're going to join us for more about the lives of stars on Thursday.
Yeah, it's great questions. And if you're curious about this stuff, we'll go into it a little deeper on Thursday. And if you want more information about what Morehead is doing in this time, please go to our website. It's www.moreheadplanetarium.org, and you can navigate to the Morehead at Home page from there. There's a whole big slate of things you can enjoy. Please follow us on social media, whether it's your Facebook, Twitter, Instagram. You can search Morehead Planetarium on YouTube and check out our virtual playlists. These sessions are recorded if you ever need to go back and reference something we talked about. And you can even treat yourself to a 360 Planetarium show on there for free. So anyway, we're happy to be with you, and we'll leave you with that, and we'll see you next time.
Bye. See you Thursday.